Okay, so this is the November 2018 paper 2 for the Matric chemistry. It says, which one of the following is the structural formula of the functional group of the ketones? So the important thing to remember with the ketones is you can see we've got 3 carbon double bond oxygen, okay, which is what we have to look for with the ketone. But the fact is the ketone must be having chains on either side of it, because if we have a carbon with a double bond to an oxygen and a hydrogen, then we will have an aldehyde. So the answer here has to be C, because this is the only one that indicates that there must be a carbon chain on the other side. If I came to this A, which looks correct, I can put a C here and an H here, and I've just turned it into an aldehyde. So that's why this one is out, and this one is out because it was already the aldehyde, and then obviously this other one is an alcohol. So we want the C. Now it says, which one of the formula below represents an alkane? Remember, the alkane is saturated. There are only single bonds. Okay, so if there are only single bonds, the easiest way to answer this question is to know your general formulas, and an alkane is CnH2n plus 2. So then you go 2 times 2 is 4, so it can't be this one. But if you can't do that, but it gets a bit hectic here. If you can't do that, you draw them, and you go like this. I've got 2 carbons. Oh, look, how many hydrogens am I going to have? 1, 2, 3, 4, 5, 6. Okay, it can't be this one. Okay, but the easiest thing is to use your general formula. So if we go CnH2n plus 2 for an alkane, it's 5 times 2 is 10, plus 2 is 12, so this is wrong. It's also unsaturated. The same here, this one's even more unsaturated because 8 times 2 is 16, and then we are actually subtracting 2 to get to 14. So the answer here is C. So we've got 2 C's in a row over here. But like I said, if you can't remember those things, just start drawing, but that 14 carbon one's going to take you a bit of a while. So now there's an organic compound, and it says, what is the IUPAC name of this compound? So we have to look for the longest chain, and always beware of the methyl groups. And if you look here, we have 3 methyl groups. But now we have 1, 2, 3, 4 carbons in a straight line. It doesn't matter which way we go, the longest chain we can make is 4 carbons in a straight line. So I'm immediately going to get rid of this one because it says propane. So we want one of these butane things. Then we must look, what have we got? They all agree that we are dimethyl. Here's my 1 methyl group, here's my other methyl group. Now we have to number them so that they have the lowest numbering. These 2 methyl groups are on the same carbon, so this one's got rid of because that one's claiming it's on, one is on carbon 2 and one is on carbon 3, the methyl groups, which is not true. And then we're going to pick 2,2-dimethyl butane because the numbering must always have the lowest value. So we are starting from this side here, that would be carbon 1, 2, 3, 4 will give you the lowest values. Now we're on 1.4. Activation energy can best be described as the minimum energy required to cause effective collisions. Answer is A. This one is caused by just your random kinetic energy. It's not got to do with the activation energy. Change the orientation of the reactant molecules. No, it might do that, but it's not the minimum, it's not the best definition. And increasing the kinetic energy of the reactant molecules, we do this if we increase the temperature or we add heat. So this has not got anything to do with activation energy. Okay. Which statement is correct for a system in dynamic equilibrium? And I bet half of you jumped on our friend B. In dynamic equilibrium, the reactants are not used up. We always have reactants and products together in a container in a system in dynamic equilibrium. And this B looks a lot like your definition, but there is something missing. It is not the forward reaction equals the backward reaction. It is the rate of the forward reaction is equal to the rate of the reverse reaction. So this is very wrong. That 2 little words, the rate of, are extremely important. all substances in the reaction are of equal concentration. No, you can put anything in the container and concentrations will differ, but at equilibrium, the forward reaction and the backward reaction are happening at the same rate, so the concentration of reactants and products remains the same. It's different molecules reacting, but their overall concentration will remain the same. Now we come to 1.6. It says, initially a certain amount of P was placed in an empty container. The hypothetical reaction reaches equilibrium in a closed container according to the balanced equation. Okay, this says delta H is less than 0, so we know immediately that this is an exothermic reaction. It says, at time T, temperature is increased. Which graph below best illustrates the resulting changes in the rates of forward and reverse reaction after the temperature is increased? Well, after the temperature is increased, increase in temperature always increases reaction rate. So if we look at these graphs and any of them show a decreased reaction rate after equilibrium, we are going to get rid of them. So we are immediately going to get rid of our friend A because it's got one reaction rate decreasing. An increase in temperature will always increase reaction rate. However, for an exothermic reaction, an increase in temperature increases the rate. An increase in temperature increases the rate of the endothermic reaction. Okay, and so here the endothermic reaction is the reverse reaction. So in this situation is going to increase the rate of the reverse reaction more than it's going to increase the rate of the forward reaction. So we want a graph where they both go up, but they go up differently. So this gets rid of this graph. This is usually the catalyst graph where the forward reaction and the backward reaction go up at the same rate. So now we have to just say we want both reactions to go up, but which one is the reverse reaction? Well, the reverse reaction has to be the solid line. Okay, this one is the reverse reaction and this one is the forward reaction. How do I know this? Because the forward reaction is always the fastest one because there's a lot of P in the container. So whatever's in a high concentration at the beginning, like this P over here, if you have a look here, this is the high concentration at the beginning, or the high rate at the beginning. Sorry, it's not a concentration graph. The high rate at the beginning will always be the thing that there is initially a high concentration of, which is the P. So this one must be very fast, the forward reaction. So the dashed line is the forward reaction. So we want the one that favors the backward reaction. So in this one is B, because if you look over here, the backward reaction, it goes to equilibrium, and then all of a sudden it increases a lot more than the forward reaction until we reach equilibrium again. So the answer is B. This one shows it favoring the forward reaction is favored, which is not happening when we have an exothermic forward reaction and increase the temperature. So we want the answer B. Okay, now it says reactions 1 and 2 below have equilibrium constants greater than 1. If we have an equilibrium constant greater than 1, remember Kc is the concentration of the products over the concentration of the reactants. And if we have a Kc greater than 1, it means that the forward reaction is favored. Okay, remember if we have an equilibrium reaction, we actually have a large number. What am I writing there? Kc is greater than 1. We have all of these things. Every single thing in the reaction is in the container at the same time, and they are all reacting with each other. But if Kc is greater than 1, then the forward reaction is favored. So if we look at these are all acid-base reactions. Okay, there's protons being donated and protons being accepted. And in this one, this H3X, is forcing a proton onto the bicarbonate ion and making carbonic acid. So if this H3X is forcing the proton onto the bicarbonate ion, it means that this H3X must be a stronger acid than the bicarbonate ion, okay? But if we go to the next one, where we have a proton and an H3X, sorry, not the proton, it's the hydronium ion. The hydronium ion is forcing this H2X into the acid, which means that the H3O is better at donating its protons than the H3X, because the Kc is showing us the forward reaction is happening. So in both of these, the forward reaction is happening, which means that these two are the big bossy ones that are donating their protons, which makes them an acid. Okay, so it says now, based on the reactions above, the acids in order of increasing strength are. So in the first reaction, we've got H3X and H2CO3, and it's not this carbonic acid that's forcing H3X to do something. It's the H3X that's forcing the carbonic acid to do something. So H3X must be stronger than the carbonic acid. So the only one that's got, let's have a look here, H3X, no, it's not this one. We need H3X and carbonic acid. So we're left with these three. So if H3X is stronger than carbonic acid, then this one is the only one that shows that the H3X is stronger than the carbonic acid. And then in the final reaction, it shows you that the hydronium ion is donating its proton to the H2X, forcing the H3X to form. So this makes sense that the strongest acid here is down as this hydronium ion. So the answer here is B, because you have to look at, Kc is telling you the forward reaction is favored, so who is the bossiest with their protons? Now, 1.8, consider the cell notation for a galvanic cell below. So I like to think of this, it's as easy as A, B, C. We have anode, bridge, cathode. It's as easy as A, B, C. Okay, so what is going on here? What half reactions take place at the anode? If you remember, my other favorite is oil rig, red cat. So if reduction occurs at the cathode, it must be an oxidation occurs at the anode. So we are looking for an oxidation reaction. Now remember, reduction is the gain of electrons, oxidation is the loss of electrons. So we need reactions that are oxidation reactions. Am I talking sense here? Yes. Reduction occurs at the cathode, oxidation occurs at the anode. So if we are oxidized, we are losing electrons, if I'm not mistaken. Okay, so here this reaction is gaining electrons, and this reaction is gaining electrons. So we are going to get rid of these reactions, and then we are going to be left with these two. But we know the anode is on the left, so we want the one with the nickel, and the nickel is going to the nickel ion and losing 2 electrons in the process. So it is D. Now it says, which one of the following is applicable to an electrolytic cell? Reduction takes place at the anode. No. Oil rig, red cat. Okay. Oxidation takes place at the cathode. Listen, if these were true, these two are both the same. There would be 2 correct answers if this were true, because these two are the opposite of each other, which is what always happens with redox reactions. Okay. But you can't have 2 correct answers, so it should have warned you already. We cannot use alternating current when we do electrolysis, because it changes the anode, causes the anode and the cathode to switch at the frequency of the alternating current, which is not good. So we need a battery, because a battery provides direct current, and so then we can keep the anode as the anode and the cathode as the cathode. And then finally, the fertilizer question, which has been removed from the curriculum. So if we have a look here, we are going from sulfur to sulfur dioxide to sulfur trioxide to oleum to sulfuric acid. Where do we need the cathode? We need the cathode here in turning sulfur dioxide to sulfur trioxide. So the answer is B.